A demonstration of solving a rational inequality. A critical number for an inequality statement is a value, call it C, such that f of C equals 0 or f of C does not exist. Now, some guidelines for algebraically solving rational inequalities are given here. Our first step is to get 0 on one side of the inequality, then combine all terms to have a single rational expression on the other side. Our second step is to find the critical numbers, that is, to determine the real roots to the numerator and denominator separately. Our third step is going to be to determine the sign, the plus or minus sign. For each interval, the roots divide the number line. Multiplicity of roots and end behavior, or the tail end test, is useful here to avoid calculations. And then finally, we will report the solution based on the inequality. So for example, let's say that we are to solve the following rational inequality. X minus 1 divided by x minus 3 greater than or equal to 5. So our first step is to get 0 on one side of the inequality, and then we'll combine terms so that we have one rational expression. Then we'll say that it's greater than or equal to 0. So x minus 1 divided by x minus 3 greater than or equal to 5 means that we'll go ahead and subtract 5 from both sides. That gets the 0 on one side. Then we have to combine x minus 1 divided by x minus 3 with this 5. So our first step is to get a common denominator. Our second step is to combine the numerators. Our third step would be to distribute the negative 5. And then our last step would be to combine like terms. And as you can see, we have negative 4x plus 14 divided by x minus 3, and that is greater than or equal to 0. And that is the form that we want before we continue. A rational expression, an inequality, and a 0. Our second step is to determine the roots to the numerator and denominator separately. These are the critical numbers. So we set the numerator equal to 0 and solve. This is a linear equation, so we add 4x to both sides, divide both sides by 4, and then reduce the fraction down to 7/2. So one of our critical numbers is 7/2. That's going to be the root to the numerator. Our denominator has x minus 3 equals 0, and we simply add 3 to both sides, and we have another critical number. Remember, a critical number is when the function is either equal to 0 or the function does not exist. And if I put 3 into the rational expression, I get a division by 0. So both of these have to be done, and we have to do them separately. Our third step is to determine the signs for the intervals. Now here is where multiplicity of the roots and the end behavior can prove to be very, very useful. So the roots are listed on the far left column here, 7/2 and 3. Their multiplicity is both 1, and that means that they're both going to cross the x-axis. And when you cross the x-axis, you have a sign change. That's going to be crucial for our analysis. The end behavior for this rational function has the degree of the numerator equal to 1, the degree of the denominator equal to 1. So the ratio of the leading coefficients is going to be the horizontal asymptote. So y equal negative 4 is the horizontal asymptote. Because it's negative, the rational function is going to start negative and it's going to end negative. That's what the horizontal asymptote tells us. So right here, I have 2 of my intervals with their signs already known. For those of you that prefer a more calculation style determination of signs, here is a sign chart. Notice that my intervals are divided up where my critical numbers are. That is at 3 and 7/2. The numerator, negative 4x plus 14, will be positive from negative infinity to 3. It will again be positive from 3 to 7 halves, but then it will change to negative from 7 halves to infinity. X minus 3 is the denominator, and that's going to be negative over the interval negative infinity to 3. It'll be positive from 3 to 7 halves, and then it will be positive again from 7 halves to infinity. Now, when I take the ratio of a positive and a negative, I get a negative. When I take a ratio of a positive and a positive, I get positive. And when I take a ratio of negative and positive, I get negative. Notice that the end behavior also told me that I'm going to start negative and I'm going to end negative. 3 had a odd multiplicity, which means it had to change sign. So that went from negative to positive. And 7 halves also had an odd multiplicity, so it must also change sign again, going from positive to negative. So the sign chart and the analysis using multiplicity and end behavior coincide. Our last step is to report the solution, and as usual, we will use interval notation. So x minus 1 divided by x minus 3 greater than or equal to 5, that was the original problem, has a solution from 3 to 7 halves. But 3 is not included because it makes the bottom 0. Those numbers are never included. 7 halves is where y equals 5 and y equals the rational expression x minus 1 over x minus 3 actually intersect. And that is included because the inequality has a bar underneath it. It is not strict, which means I am allowed to include intersection points. So 7 halves is allowed in the answer. And here is a graph of the line y equals 5 in purple. The dashed line is the vertical asymptote, x equals 3. And the blue graph is the rational expression x minus 1 over x minus 3. And as you can see, the blue graph and the purple line intersect at 3.5. And the rational function is above the purple line between the vertical asymptote at 3 and 3.5, where it finally intersects that graph. So graphically and algebraically, our solutions coincide. Thank you for your time and attention.